Today we are gonna focus on this topic, pipeline data path and control. It's a continuation from the previous videos. So this book is Computer Organization and Design. Basically uses ARM assembly. Sorry. So this figure shows multi-clock cycle pipeline diagrams of 5 instructions. These are the 5 instructions, as you guys can see. Load. We are loading from this address. This is memory address and this is the register address. These are the clock cycles. So when the clock cycle advances, the instruction moves from one stage to another. This is instruction memory, or we can say, yeah, it's instruction memory. This is data memory. This is the register. There are two registers just because in one register we are reading the instructions, uh, reading the registers, the data from the registers from the instruction memory, and in this read we are gonna perform write operations as explained in the previous videos. The write, if the right hand side is not shaded, then it means we are gonna perform a write operation, and if the right hand side is shaded, it means we are gonna perform read operation. If it's shaded, that means everywhere we are gonna perform read operations. So, as you guys know, load instruction uses all 5 stages. And so first we fetch the instruction from the memory, then we store it in IXID stage, or the data we get from it. The instruction basically we're gonna store it in IXID stage, and then we're gonna read the registers. Basically, it's having, then whatever the values we get from those registers, we are gonna store it in ID EX stage. Yeah, this is EX stage. EX stage is nothing but execution stage where our ALU unit lies. And then those results we are gonna forward. Also, one thing I okay, let's continue this first. Uh, Whatever the result we'll get, we're gonna forward it in this EXMEM stage. Um, these are nothing but the pipeline registers. We're gonna store the result which we get from our previous operations. We are gonna store it in these registers in order to reuse in case if they are needed, and then we advance to further, which is nothing but in this operation we are gonna perform read operation from the memory as it's a load instruction. Mm, Once we load the data, we are going to store it in this mem RW, which is something but write backstage. That's given in the previous previous pages. They have mentioned all the stages. You guys can go through it. Similarly for subtract here, things work pretty differently because this is our format instruction. So the the main thing, or we can say the systematic approach for these instructions is the same for subtraction instructions. So you guys can go through the text once, it will be more clear to you guys. as these instructions and are not dependent on each other, so we don't see any stalls in here. Stalls is nothing but some, you can say, the bubbles which they have described in the previous topics. We'll come to it later on. So what they are saying is, this thing is not just happening in a single clock cycle, and it's obvious that in each clock cycle it's moving ahead, as you guys can see there. It takes around 5 clock cycles to write the loaded data from memory to write it into register. So in this diagram, they have clearly mentioned the stage names and the instructions which we are going to process in the processor. The execution order of the program is from top to bottom, but the data or the instruction flows from left to right, as shown uh, with time. And this is pretty straightforward. There's nothing complex in it. Uh, Instructions. This is the traditional uh, traditional representation of data path, which doesn't use um, separate data part for each instruction. Everything is embedded in this in a single clock cycle diagram corresponds to clock cycle 5 of the pipeline. This figure, as you can see, in a single clock cycle, figure is vertically sliced through a multiple clock cycle diagram. This is diagram for multiple clock cycle, and this is for single clock cycle. And as you can see, when load instructions come, when this first load instruction comes to or advances to write back stage, the uh, add instruction, the last add instruction reaches the instruction fetch stage, not reaches, enters the instruction fetch stage. So, yep, as I said, see here we can find the load instruction which is in write back stage at present, and then uh, we can just map out from this the previous figure, write back stage, instruction fetch, and at the same time, if we see this correct instruction which is in memory phase, see, it's clear. I don't think it's that complicated. I hope you guys understand it. Mm. In this way, this is a single clock cycle diagram. We can say it as a state at one particular instance. The data bit will look like this. It will be filled with instructions. And each instruction performing some logical operation in the logical unit they are present. Let's move on. And this is few students are debating whether uh, a group of students were debating the efficiency of five-stage pipeline when one student pointed out that all instructions are active in every stage of the pipeline. After deciding to ignore the effects of hazard, they made the following four statements. Which one ones are correct? We gotta figure it out. Which one is the correct? Nine branches and an instruction to take fewer stages than the five required by the load instruction will increase pipeline performance under all circumstances. Um, and the next one is trying to allow some instruction to take fewer cycles. Since the throughput is determined by the clock cycle and the number of pipelines, pipe stages, or instructions affects latency, not throughput. You cannot make ALU instruction have take fewer cycles because write back for result branches can take fewer cycles, so there is some opportunity for improvement. And the fourth one is, instead of trying to make instruction take fewer cycles, we should explore making pipeline longer so instruction take more cycles, but cycles are shorter. This could improve the performance. I'm gonna go with the third statement, guys. Let's check it out. Let's use AI to tally our answer. Check which one is more logically correct. I'm gonna go with third one, as I said before. I'm not sure, but let's until it generates the answer, we'll move to the pipeline control topic. I hope guys uh, just read with me. Oh, we are wrong here. The statement 2 is correct one, and the reason is yep, I think that's logically valid. And even if we reduce the time for a single stage, um, still the throughput gonna be one instruction per cycle since we are having one pipeline. So it doesn't matter if we wanna lower the time taken by a single stage, as you guys can go through this text as clear. So in the next video we uh, will go through some pipeline control topic. For now we are gonna end our video here.